Thank you. So today I'll just talk about some preliminary results of running on the GPU nodes. We just got a new set of GPU nodes, P100 based GPU nodes on Comet. So we are basically testing right now. That's the machine itself, Comet. It's a big collaborative effort, UCSD, SDSC, IU, and all the vendors, Intel, Aeon providing our storage, and Mellanox for the interconnect, and NVIDIA GPUs, and it's an NSF-funded project. It's basically a 2.1 petaflop total peak machine. Primarily, it's 1944 compute nodes with Intel Haswell processors. We have 72 GPU nodes, so today's talk is mostly about what I did on the GPU nodes. 36 of them came up with the initial deployment that was with 2 NVIDIA K-80 cards in each node with dual Kepler GPUs, so you get 4 GPUs per node. And we just put into production in July 36 new nodes with basically NVIDIA P100 GPUs, and we have 4 GPUs per node. In addition to that, we have a few large memory nodes. The topology is a hybrid factory. We have a 4:1 oversubscription cross-rack. In terms of storage, we have about 7.6 petabytes of storage, 200 gigabytes per second pushing through the network. And we do actually have a durable storage option, which we use to basically snapshot critical data. So moving on to what we have on the system, we run a lot of flavors of MVAPICH. I mean, the default MPI on the compute side is MVAPICH2.1. We do have that MVAPICH2X install. Today's results are all going to be with the MVAPICH2-GDR 2.2. And I tested both on the K80s and P100s. In addition to the MVAPICH stack, Dr. Panda's group here has, at the HIBD lab, they develop RDMA Hadoop and RDMA Spark, and that's also available on the machine. So moving on to the architecture. So we basically have 2 sets of nodes, as I mentioned, in terms of GPUs. So the K80 node, let me see if I can point. So GPU 0 and GPU 1 can do GPU direct, and then GPU 2 and 3 can do GPU direct, and the network card is on the socket with the same socket as GPU 2 and 3. So you can imagine this can lead to some interesting issues and optimizations that have to be done. I think Harry looked at this and said, "That's interesting. We do a lot of things." And to make things fun, when I get to the P100 architecture, you'll see the adapter is on the other side for the other P100 nodes. So I started off by doing standard OSU benchmarks, and these are basically with the out-of-the-box tunings for the MPI. So if you look at this is for an intra-node test on the K80 nodes. So what I'm comparing is using 2 GPUs on the same socket, so GPU 2 and 3 are on the same socket, and then using GPU 1 and 2, which are on different sockets. So you can see the latency for the second case with the GPUs on the same socket is lower as you expect, 2.82 microseconds, and then between 1 and 2, it's 3.18 microseconds. And the difference kind of continues all the way up to the big message size. I think it's 256K there. Similar story with bandwidth. And again, this is out of the box. So you'll see this dip here. I think that's right at the 8192 GPU direct, right after that, I think. So if you look at the case where the GPUs are on different sockets, you can see the bandwidth tops out at about 8 gigabytes per second with the 4 meg size. And when I get to the case with the GPU 2 and 3, it tops out at around 10,000 so 10 gigabytes per second. So similar thing when you go on to the internode, there are lots of different combinations we can try. So what I was doing was binding the MVAPICH process, the MPI process using the CPU mapping to CPU 0 and then GPU 0. So that's actually the case where you're not on the HCA socket with both the CPU and the GPU. In this case, you have the CPU binding on the socket that's not on the HCA, but the GPU is on the HCA. And then in the last case, you have all two on the, all of them on the same. So you can see the progression in the basic increase in the latency. So it's 2.27 microseconds if you're on the socket with the HCA, and then it picks up to 2.43 and 2.47 and that. So this is quite expected. This was a little unexpected. So I did the same thing with the bandwidth test, and I think this is something we may have to go find out what particular parameter we have to tune to get that need to come back. But if you look at, so it's the same case. Basically, you have three cases: a GPU on the same socket as the HCA, GPU, not on the same socket as the HCA, and then the other two where it's on the same socket. So you can see the bandwidth-wise, we top out at around 6 gigabytes per second, which is the IB. We have FDR InfiniBand, so that's where we top out. So going on to the P100 node architecture. So now it's a little different. Oh, and by the way, I don't know why this is this way, but we also have the CPUs, all the evens on one socket and all the odds on another socket. So it makes it really interesting when you're trying to write a wrapper to bind tasks the right way. So now in this case, the network adapter is actually on the socket with GPU 0 and 1, and so it's flipped basically. So very similar results in this case. So if I go to, so again, the same thing. Now 0, 1 is the case where you're on the socket with the HCA. So it's a little different. And then 2, 3 is on the socket without the HCA. And then 1, 2, you're basically going across. So this is intranode. So you get a latency of 2.73. So it's a little bit lower than what we saw on the K80s. I think about 100 nanoseconds lower probably. And then the latency between the 2 and 3 is 2.95, and then 1 and 2, because they're on different sockets, goes up even more. Internode bandwidth, again, if you look at the cases where both the tasks are on the same socket, you go up to close to, I think that's 12.2 gigabytes per second. And the case where they're on different sockets, you top out again at around 8 gigabytes per second. So that's a similar result to what we had on the K80. So looking at the latency results, internode, again, this time I didn't do all three combinations, but in the case where it's off the socket, it's about 2.35 microseconds, and then on the socket with the HCA, you get 2.17, which I think is what's published also on the MVAPICH side. So we are doing okay with the case where we are on the same socket as the HCA. Similar cutoff at the, I think it's 256 kilobytes, I think, is where again you see the same kind of jump, and then we top out at 6 gigabytes per second. So that was kind of the baseline of how things were doing. So one of my first concerns was, okay, what does it do to the application when you see something like this and you're using all 4 GPUs? Because that could be an issue at least for some applications. So for today's talk, I basically have 2 sets of benchmarks, one with the HOOMD-Blue cases, So I picked up 3 benchmarks. These are the standard benchmarks from the site. So Lennard-Jones, decahedron, and hexagon benchmarks. So the first case is with 64K atoms and basically the Lennard-Jones pair force. So here I was trying to do a few things. So one is scale out the number of GPUs, but then when I get to the higher GPU counts, I was also trying to see if I can split them across 2 nodes or keep them on the same node. So for the Lennard-Jones case, I didn't do that, but you'll see in the results that are coming that's of, yeah.
Is the GPU number the number of GPUs per node or
Total. So what I was doing was using the 2 GPUs on the HCA to do one set of scalings and then go back and do a case where I use all 4 GPUs and see how things go. So you can see in this case, the scaling kind of stops at 4 GPUs. But if you go to the next case, which has a little bit more, it's a larger size. Now here what I'm doing is, again, 1 GPU, 2 GPUs on the same node, 4 GPUs on the same node, then 4 GPUs split across 2 nodes. And this is with the 2 GPUs on the HCA. So that's the best case scenario in terms of distribution. And then going out to 8 GPUs, again doing the same thing, splitting it across 2 nodes and then going all the way out to 16 GPUs using all 4 basically. So you can see it's scaling pretty okay in terms of with the GPU count, and for the smaller number of GPU cases, actually going off node or using all 4 GPUs on the same node seems pretty much very similar in performance. So at least in this case, not having the GPU direct the performance across the 4 GPUs didn't really hurt us. Similar thing with the P100 nodes. Again, when you look at the 2 GPU case, I didn't mention, basically that y-axis is the time to solution in hours, and that's what's measured in the benchmark. And I think it's for 1 million steps, if I'm not mistaken. So number of nodes is number of nodes, GPUs on the x-axis. So basically, again, doing the same thing, it's scaling okay in terms of the GPU count. And you can see, very similar to the K80s, it didn't really affect us in terms of whether the GPUs were on the same node or across nodes. So the last HOOMD-Blue benchmark was basically with the hexagon benchmark, which is a slightly, I think it's even a bigger case than the other 2. And you can see it scales pretty well, going out to 8 GPUs and using, again, basically 2 nodes with 4 GPUs or 1 node with all 4 GPUs, you get pretty much the same performance. So at least we're doing okay with this application. So the other thing I was trying was the OSU-Caffe test cases. So today I have the results for the CFAR10 quick case. This is preliminary results with the K80 nodes. Here what I did is kept all the data in the database in the Lustre file system. And I was talking to Amar, and he was saying, oh, the SSDs probably do a lot better. So this is something that I'm going to try in the future, because we actually have 280 gigabytes of SSD on each GPU node. So we can try scaling out and see with a bigger problem and see how that does. So in terms of scaling on the K80 nodes, it does pretty well. Pretty much using all 4 GPUs didn't hurt even in this benchmark. And I guess what I have to do is go back and look at the profile of these communication patterns and see where we are falling in that, and how much of the benchmark time is actually spent in communication. But for this small test case, we are doing pretty good. I think we have the largest data set. I think the AlexNet and the ImageNet data set downloaded, so I'm going to try that out of the SSDs next and see if that scales out to more GPU nodes. So right now I stopped this at 2 GPU nodes. So that was basically all the benchmarking that I've done so far. The P100 nodes are quite new, so I think there's a lot of tuning and additional stuff to be added there. So I think there's work to be done there. To summarize, basically, the OSU benchmark results, they're showing expected results when we are on the GPUs associated with the same socket, and if you have the HCA on the same socket. Going off after the second socket did have an impact, so that's something that we can look at in terms of tuning parameters. So out of the box, it's not doing that great. So, and then the strong scaling results for HOOMD-Blue, it looked like, at least for the cases that I was looking at, splitting the number of GPUs on same number of GPUs on multiple nodes or having them all on the same node didn't impact the performance as much. The OSU-Caffe scaling looks pretty good, and it's promising. And if we can move the data to SSD, where the I/O performance should be a lot better, then we should see if the performance improves, and that's something that we're going to do in the future. And last thing I want to say is thanks to the MVAPICH group for excellent support for over the years. I think all our machines have had MVAPICH as the default, and we've always had quick feedback, quick fixes during the night. I don't know when DK's group rests, but I really want to thank the group for supporting the installations on the SDSC machines. Thank you.